All right, so we're going to find the area between these curves. So we're going to start with this one is a line, which is g of x. So that's this line, and if I were to do the integral from 0 to 3 of x plus 2 dx, I would get this area. This is a parabola, and if I did the integral from 0 to 3 of this, x minus 1 squared plus 1, a parabola moved over 1 and up 1, and found the area between 0 and 3, that would be the area under the parabola. But what if I wanted to know the area between the curve and the parabola, as this shows? Well, that would be this trapezoidal area minus the area of the trapezoid that's under the curve would give you the area of the trapezoid that's between the two curves, if I subtract this from the whole trapezoid. So if I take this area minus this area, I would get the area between, which would be the integral from 0 to 3 of x plus 2 minus x minus 1 squared minus 1, or minus this whole quantity, dx. And if I simplify that first and then integrate, I would have the area between. Okay, so that's how you do that kind of problem. Now, this kind of problem. They give us some practice problems here. So I was doing this and got interrupted, so I'm going to erase what I did here. Okay, so we're going to do the area between the square root of x and 1/4 x. So the square root of x goes up for 1, it's up 1. And the square root of 4 is 2. The square root of 9 is 3. And the square root of 16, this is 8. This is about 16. Square root of 16 is 4. So it goes. That's this y equals the square root of x. And then 1/4 x. So if it goes over 4, it's up 1. 8, it's up 2. 12, it's up 3. And 16, it's up 4. So it intersects there and at 0, 0. So that's y equals 1/4 x. So to find the area between these curves, first of all, I need to know which one's on top. I've determined that. I need to know where they intersect, and that's at x equals 0 and at 16. So the area between the curves, the region bounded by these two curves, is the integral from 0 to 16 of the upper curve minus the lower curve. And you can do the antiderivative and evaluate from 0 to 16, or you can just type this into your calculator and it'll calculate. Graph this and then find the area between 0 and 16. Now they give us another one, so let's take a look at that. That's y equals 12x minus 2x squared. And x squared minus 8. So the first one is an upside down parabola starting at 12 and a little bit skinnier than normal. And the second one's starts at minus 8 and it's the normal width. So it's probably going to intersect in places down here, and they're probably going to be equal and opposite. And to find those x values, we're going to set the y value of this has to equal the y value of this when these run into each other. So we're going to set x squared minus 8 equal to 12 minus 2x squared. So we would have, if I add 2x squared to both sides, and add 8 to both sides, divide by 3, take the square root, and when I do the square root, it's plus or minus. So here's the minus and here's the plus. Now, if I want to make this a little easier, well, let's finish this here. So then I would do the integral from minus square root of 20 over 3 to plus square root of 20 over 3 of the upper one was this upside down parabola minus the lower one, which is x squared minus 8. Now, I know that this is very symmetric, so I could go from 0 to there and double my answer too. So that's another possibility, is to go from 0 to the plus 1 and double my answer. That makes it a little less messy and a little easier to do. Okay? Anyway, I worked that out in class, and you can work that out, or you can just type this into your calculator and you get a decimal approximation. Yeah. Now I'm going to do C. So I'm going to need another sheet of paper here. And it says the area bounded by cosine of x and the sine of x. Cosine of x starts at 1, goes to 0 to minus 1 by pi. And the sine goes from 0 to 1 and back to 0 by pi. And they intersect at some place where the x and y coordinates are the same on the unit circle. And on the unit circle, cosine's the x coordinate, sine's the y coordinate, and they got to be the same, which happens at pi over 4. So this is pi over 4. And so to find the area bounded by the curves and the y-axis, so this is the y-axis, and the curve is this area. So we do the antiderivative, the integral of from 0 to pi over 4. The upper curve is the cosine of x, minus the lower curve is the sine of x. And we would do those antiderivatives. This one's pretty easy. The antiderivative of cosine is sine. Antiderivative of negative sine is cosine. Evaluated from 0 to pi over 4. So if I put in pi over 4, they're both square root of 2 over 2. So we get the square root of 2 over 2 plus the square root of 2 over 2, which is just the square root of 2. Minus, we put in 0. Sine of 0 is 0. Plus cosine of 0 is 1. So we get the square root of 2 minus 1. Decimal approximation is 0.414. You could type this in you could graph this and then calculate that area under the curve, and you should get on the calculator 0.414. Okay, and let's go to another one here. This is between that one, and so this one gets a little tricky. We have to be careful on this. Y equals x to the third minus x, and y equals x squared. And if you graph this, you get the cubic doing something like this, and the quadratic doing something like this. So there's some area between the curves on this side and some area between the curves on this side. Now, so we're going to have to split this up into two integrals because this one's above this one for part of it, and then they switch roles. The parabola is underneath, and then the parabola is over the top. So we have to integrate from here to there with doing the cubic minus the quadratic, and then from here to here we have to do the quadratic minus the cubic. So we have to find those places first. So we set these equal. So we have x to the third minus x equals x squared. Subtract x squared from both sides. And you could graph that and find out when it's equal to 0, but let's do some factoring. First of all, you take out what's common, which is an x, and you get x squared minus x minus 1. And to solve a quadratic, we use the quadratic formula. See, a is 1, b is -1, c is -1. So we've got x equals, of course it equals 0 from that, but we also have it equal to the opposite of b, so -1 becomes +1, plus or minus -1 squared, b squared, minus 4 times a times c, so minus times the minus is plus, and 1 times 4 is 4, all over 2a, which is 2. So they intersect at 1 minus the square root of 5 divided by 2, 0, and 1 plus the square root of 5 over 2. So to do this, we do the antiderivative or the integral or find the area under the parabola minus the area under the cubic from 1 minus the square root of 5 over 2 to 0. So we're taking little slices this way, dx slices, and we're taking the upper curve minus the lower curve. Then we have to add to it this area, which is going to be from 0 to 1 plus the square root of 5 over 2 of the parabola minus the cubic. Slicing little slices of dx. And you can run that through the calculator, or you can actually do the antiderivative of this and evaluate it with those limits, and you'll get the answer to D. I'm more concerned, can you set it up right now? Okay. So now, we're going to go to the next problem, which is, come on here, what if the curves are going sideways? Well, if it's going sideways and we do it vertically, then the top and the bottom are the same equation, except I'd have to solve for x. And if I take x minus y squared plus, x equals y squared minus 1 and solve for x, it'd be x plus 1 square root plus and minus. So I'd have to do the plus 1 minus the minus 1 from, looks like minus 1 to 0. And then I'd have to do the plus 1 minus the line from 0 to 3. And I could do it that way, but I'm going to have to do it in two different sections. This section where this is the high curve, that's the low curve. And then this section where this is the high curve and that's the low curve. However, if I go sideways and take slices this way, I can do it. I can consider it, if this is the positive side is that way, this is what I would call my high side and my low side. It's my right is the positive high side, which would be the line minus the parabola. And that's what they're recommending you do on this. So we would take the integral from -1 to 2. It's where they intersect of the high one, which is the line, x minus 1, minus the parabola, which is the, which is y squared minus 1. Oh, but if I'm doing little slices this way, which are dy's. And so I need this to be in terms of y. So if I add 1 to both sides, I get y plus 1. Now it's in terms of y, dy, so I can just integrate that and figure out the area between the two curves. Okay. And so then they give you the formula. If it's going sideways, you do the rightmost minus the leftmost curve, and you do y's and dy's. The slices are in terms of y's. Okay, and they give us some practice problems on that. So let's do the first one. So if we have x equal y squared, that's a parabola. Goes through 1, 1, and 4, 2, and 4, -2, and 1, -1. That's the first one. And the second one is a upside down, or in this case, opening to the left, goes through 6 and opens down. So we need to know where they intersect, and we'll do, if we do it this way, we have to go from the positive to the minus and the positive to the minus square roots, and we have to solve for the square roots. Makes a messy integral, but if we go slices this way, then it goes from this point to this point, and it's always this curve over that curve, or minus that curve. So we'd have the integral of this curve, which was 6 minus 2y squared, minus this curve, dy, because my slices are little dy's. And I have to integrate from something to something, and I have to know where these intersect. These are very symmetric, so if I can find the one, it's going to be from the minus to the plus. Or I could go from 0 to the plus and double the answer. Got some symmetry here, so I could do that. But let's go ahead and figure these intersections. So one way to do it would be to, since y squared is equal to x, I could put x in place of the y squared, and I get x equals 6 minus 2x. Add x to both sides, we get 3x equals 6, and x equals 2. So 2 is where they intersect, and if x is 2, y is the square root of 2 plus or minus. So this is the plus square root of 2, and this height is minus the square root of 2. So I can go from minus square root of 2 to plus square root of 2, or from 0 to square root of 2 and double my answer. C. So we have y equals x squared, regular parabola. and y equals 2 minus x, which looks like this. And the area bounded by this, by the x-axis, the parabola, and the line, and the x-axis. So where do they intersect? But basically, I'm going to do slices this way, or I could do slices this way. And this way, if this way, I'd have to do two integrals from here to here under the parabola, and then from here to here under the line. If I do it this way, I only have to do one integral, and that's from 0 to wherever they intersect. Let's see, where do they intersect? This would be y equals y and x. No, wrong equation. This one. I think this one goes through 1. If x is 1, it goes 1, 1, and this one goes through 1, 1. So this is 1, 1. So I want to integrate from 0 to 1, if I'm doing it in dy slices this way, horizontal slices. I'm going to go from 0 to 1 in the y of the line, which now I have to solve in terms of y. So I add the x, subtract the y, and I get 2 minus y. The line is the more right, the less. The left is the parabola, which is, if I solve for y on that, it's going to be minus the square root of y. I mean, solve for x, it's going to be square root of y, and we're going to use the plus side, not the minus side. And this is what we'd integrate to get this area here. Now, once again, you could also do it from 0 to 1 of the parabola, doing vertical slices, plus the area from 1 to 2 of under the line, which would be 2 minus x. They're wanting you to be able to think of it two different ways on that. And how about between these two curves? Well, this is a little harder to solve for the y and do it vertically. So this one is a parabola somehow this way. Let's see, it goes through 2 and 0, 0 and 2. So it probably goes through, and yeah. That's the first curve. And then the second curve, y equal x, looks like this. So this is minus 1, 1, 0, 2, and then this is 3, 3, 3, I believe. We could confirm that by setting these equal. We'd have y squared minus 2y equals y, because these are x's are equal, so these have to be equal. Subtract y from both sides, and we get y squared minus 3y equals 0. We factor out a y, and we get y times y minus 3 equals 0. So 0 and at 3 is where they intersect. So we do the antiderivative, the integral, find the area between the rightmost is the line, y, minus, we're doing it in slices this way, so they're dy's, and we're going to do that minus the parabola, which is y squared minus 2y. We're going to integrate from 0 to 3. And that's how you would set up that one. Now, arc length. If we have a curve and we want to find how long this curve is, we can do estimations. We can start someplace and go to someplace and figure out the straight line piece and not the curve length. by saying it changes so much in the x and it changes so much in the y. So an approximate length of that would be the square root of delta x squared plus delta y squared. That's the length of the line, which is close to the curve. Now, I'm going to factor out a delta x out of the inside here and keep it inside. So it's going to be, I'm going to factor out a delta x squared. So it's going to be 1 plus delta y over delta x squared. And I can take the delta x out of the square root, so it'd be delta x on the outside. And inside I'd have 1 plus delta x over delta y, which is the slope, which is the derivative, but I'm just going to write delta x over, or delta y over delta x squared. And then if we make the changes really, really small, which is dx and dy, then this would become, in the limit, it would become the square root of 1 plus dy dx squared dx. And dy dx is the derivative, and so hence we have this formula for the length of an arc between A and B. We add up all these little tiny pieces. We make little smaller amounts and moving across. So they say here, find out the length of the arc on y equals x squared. We know what that looks like. From -1 to 1. How long is that line? And so you do the integral of the square root of 1 plus the derivative of x squared is 2x squared, evaluated from -1 to 1 dx. And if you pull out your calculator and just plug that in and then find the area under this curve, that'll tell you how long that arc is. Then they say find the area under this one. Well, if you square both sides, you get y squared equals 4 minus x squared. If you add x squared to both sides, you get x squared plus y squared equals 4, which is the equation of a circle of radius 2. So if you want the arc from -2 to 2, you're going to get half the circumference of a circle. And the radius is 2. The circumference of the whole circle is 2 pi r, so that'd be 2 pi 2 or 4 pi. That's all the way around. So the answer to this one should be 2 pi. And we would integrate the derivative of this. So we have the square root of 1 plus this derivative, which is 1 over 2 square root of 4 minus x squared times the derivative of the inside, which is minus 2x squared, evaluated from -2 to 2 dx. This would be a very big mess to try to integrate, so we can just type this function into the calculator, find the area from -2 to 2 under this curve, and we'll know how long this arc is, and it should come out to be 2 pi, 6.28-ish. C. Running out of room here. Let me pull in another sheet of paper. The arc length of y equal x e to the 3x on the interval from 0 to 1. And so we would do the integral from 0 to 1 of the square root of 1 plus the derivative of this. So that's a product rule. So derivative of x is 1 times e to the 3x plus the derivative of this, which is 3e to the 3x times the derivative of the first times x. All of that squared dx. So once again, I would type this into my calculator and find the area between 0 and 1, and that would be the length of the arc on this curve. Okay? And you can see that we're getting square roots of messy stuff, and they're typically ones that you'll just be hard to do the first fundamental theorem of calculus, first theorem of calculus. You would use probably a technology to do it. And this one, okay, so we're going to do E now, which is kind of a tricky one. It says a moving particle is traveling along a curve, and it's on this curve, which is a parabola that's up 1 and compressed vertically, so it's really wide. And this particle is traveling on this curve at 7 centimeters per second. And it travels on this curve for 4 seconds. So it's gone 28 centimeters in this curved path. So they want us to find the location that it's at, given that it starts at 0 and f of 0, which is, if you put 0 in here, you get 1. So it starts at the place 0, 1, ends up here, following this path. Now, to find the length of an arc on the curve, you do the antiderivative, the integral of starting from where it starts to where it ends, which we have no idea. It's not 28 because that would be straight out, and this is curved up, so it's not 28. And we have to do the square root of 1 plus the derivative, and the derivative of that is 0.2x, 0.2x. That derivative squared dx. So all we have to do is figure out when that length of arc is equal to 28. But having the end of this unknown and getting 28 is a little different than what we've done before. So we need to get the antiderivative of this. So we're going to pull out our tables. Hopefully we'll pull out our tables. Here we go. And try to find something that looks like that. So it's the square root of an a and a variable squared. So it's plus, it's a square root in the numerator, which looks like 17. So I'm going to set this right there. So it's going to be related to this, but we've got u, and we have 0.2x, and it's supposed to be a u, and it's plus, so we're not doing the minuses on any of these. We're doing the plus ones, the top one. So we're going to have to do a u substitution. U equal 0.2x, so du is 0.2 dx, and we're going to divide by 0.2. So this integral will change to new limits, don't know what they are, of the square root of, and it's 1 plus x squared, or u squared, but I can go the other way around, u squared plus 1, and dx is du over 0.2, which I can put out here. And I want this to equal 28. Now I could multiply both sides by 0.2. And that would be all right. So then I'd have the integral from something to something, because that's u limits, not the x limits, 0 to b. So I'm going to change back to x, so I'm not going to worry about finding what these limits are. And it's going to be the square root of u squared plus 1 du equals 0.2 times that would be 5.6. Is that correct? Going to multiply by 2 is 56, and 0.2 would make it 5.6. So this is what I need to solve. Okay? Now, using this formula, 17, this becomes the we're doing the integral right now, so it's going to become u over 2, and u is 0.2x, so now I'm going back to my x's, 0.2x over 2 square root of u squared plus 1 plus a squared, so that's 1 squared or 1, over 2 ln u plus square root of u squared plus c, but we're doing a definite integral. I'm now back into x's, so it's from 0 to what I want to find out, and it's got to be equal to 5.6 since I took the 0.2 over. So I'm going to type this into my calculator and find the area between, I'm going to find out when this becomes, let's slow down, say it carefully here, Miller. I got to put in b into this, so all the x's would be b's, and then I got to put 0 in. And 0 times all of this is going to make that be 0 when I put 0 in. This would be 0 plus 1, which is 1, and ln of 1 is 0. So if I put 0 into this, I get 0. So it's minus 0, and then b in for all the x's. So this has to equal the 5.6. So I'm going to type this into my calculator, which I think I've already done, except I kept the 0.2 when I did it. So I'm going to take that out. Go to my graph. I have 1 over 0.2, and I'm going to take that out. So I have the 0.20x over 2 square root of 0.2x squared plus 1, 1/2, and then continuing on over here, 0.2x plus that. And I don't need absolute value because we're staying in the positive side. We're over here in the positive, so don't need to worry about that. And I want to know when it's 5.6. So I'm going to graph on zoom 6. There's this side with that, and there's the 5.6. It intersects further out, so I have to go to my window and go to bigger x's, like to 20. And now I graph. That's this side. There's the 5.6. So I'm going to go second, calculate, second trace, find the intersection between that curve, enter, that curve, enter, and my guess, I'm just going to say wherever it was, and it says it intersects at 14.91. So x has to equal 14.91656, and my y is 5.6 high. But this is not this curve. Going back to what they asked us to do, they wanted to find out where it ended up. Well, the x value of where it ended up is at 14.91656. The y value would be whatever I get when I plug that into the original equation, which was 0.1 x squared plus 1. So I got to put 0.1 times this squared plus 1 to find the y value of where it's at. And that would tell me its position of the particle after 4 seconds, after it's traveled 4 times 7, 28 centimeters along the curve.